Welcome everyone. In the previous chapter, we were discussing the topic Fourier transform and Fourier series. In today's video, we will discuss the various symmetry conditions for a given function ft. When a given function is such that it possesses certain symmetry properties, then it is possible to tell by inspection what terms will be missing in its Fourier expansion. Also, the expressions for the Fourier coefficients of those terms that are present in the Fourier series can be simplified directly. That is, certain symmetric conditions of periodic functions provides a shortcut for evaluating the Fourier coefficients as given in the following table. Let us discuss all these symmetry conditions one by one and find out the characteristic properties, the values of the various coefficients of the given function. The first condition for symmetry is when a function ft will be equal to f of minus t. If this condition is satisfied, that the given function will be known as even function. So, if a given function is an even function, that is if value of ft is equal to f of minus t, then that function will contain only cosine terms. Value of a0 by 2 will be equal to average value of ft over a period t. The value of an will be given by 4 by t integration ft cos n omega t dt from the limit 0 to t by 2. The value of the coefficient bn will be 0. An example of such a function is given in this figure. From this figure, we find that this is the amplitude of this function, this is the function, and this is the time axis. From this figure, we find that f of t will be equal to f of minus t. So, this is an example of an even function. So, if a function is an even function, it will contain only cosine terms, that is the value of bn will be equal to 0 in this case, and the value of a0 by 2 and an can be found out by this expression. And we will substitute the value of bn equal to 0 for such type of function. Now, let us consider the second condition of symmetry. The second condition for symmetry is when the value of the function ft will be equal to minus f of minus t, then that function will be known as an odd function. So, if we have an odd function, then its Fourier series will contain only sine terms. That means that the value of the coefficient a0 by 2 will be equal to 0, the value of an will also be equal to 0, and the value of bn will be equal to 4 by t integration 0 to t by 2 ft sin n omega t into dt. And this figure shows an odd function. Here we find that the condition f of t is equal to minus f of minus t. So, this function is an odd function, it will contain only sine terms. So, we have to find out only the value of the coefficient bn in this case, which will be given by this expression, and we will simply substitute the value of a0 by 2 and an equal to 0 in the Fourier series of such type of function. The third condition for symmetry is when ft will be equal to f of t plus minus small n t by 2, where n is odd only. If this condition is satisfied, then the characteristic properties of such a function is that it will contain only even harmonics. Both sine and cosine terms will be present in this case. So we will have to find out the value of an, bn and a0 by 2. In this case, the value of a0 by 2 will be equal to average value of ft over a period. The value of an will be found out by this relationship, 4 by t integration 0 to t by 2 of ft cos n omega t dt. The value of bn will be given by this relation, 4 by t integration 0 to t by 2 of ft sin n omega t to dt, and this is the example of this type of function. Here we find that from this figure we find out that f of t will be equal to f of t plus nt by 2 and also f of t minus nt by 2. So in this case we will have to find out the value of all the three coefficients using these three formulas, and by substituting all these three values in the given expression for Fourier series, we can find out the Fourier series for such type of function. The fourth condition for symmetry is that when f of t is minus f of t plus minus nt by 2 for n odd only, then only odd harmonics will be present. Both sine and cosine terms will be present in this case, but the value of the coefficient a0 by 2 will be equal to 0, and the value of an and bn will be found out by using these two relationships. An example of such type of function is as shown in this figure. From this figure we find that f of t will be equal to f of t minus f of t plus nt by 2 and minus f of t minus nt by 2. So in this case only the value of the coefficient a0 by 2 will be 0 and only the coefficient an and bn will be present in this case. The fifth condition for symmetry is that when ft is equal to ft will be equal to f of minus t and also ft is equal to f of t plus minus nt by 2 for all odd n, that is both these conditions. If both these conditions are satisfied, in such a function will have only even harmonics and only cosine terms. The value of a0 by 2 will be the average value of ft over a period, and in this case the value of the coefficient an can be found out by integrating the function ft cos n omega t dt within the limit 0 to t by 4. So the value of an will be equal to 8 by t integral 0 to t by 4 ft cos n omega t dt, and the value of the coefficient bn in this case will be 0. An example of such type of function is as shown in this figure. This function satisfies both the conditions, that is f of t is also equal to f of minus t and f of t is also equal to f of t plus nt by 2 and f of t minus nt by 2. So in this case only the value of the coefficient bn will be 0 and the value of a0 by 2 will be equal to the average value of ft over a period, and the value of an will be equal to 8 by t integral 0 to t by 4 of ft cos n omega t to dt. The last condition for symmetry will be satisfied when a function ft is equal to minus of f of minus t and also ft is equal to minus of ft plus minus nt by 2 for all odd n. In this case we will find that the function will have only odd harmonics and only sine terms will be present in that case. So the value of a0 by 2 will be 0, the value of an will also be equal to 0, and the value of the coefficient bn will be equal to 8 by t integration from 0 to t by 4 of ft sin n omega t into dt. An example of such type of function is as shown in this figure. From this figure we find that for this function ft, f of t will be equal to minus f of minus t and also f of t will be equal to f of minus f of t plus nt by 2 and minus f of t minus nt by 2. So in this case we will have to calculate only the coefficient, Fourier coefficient Bn using this formula, and we will just substitute the value of a0 by 2 and an equal to 0, and we can find the Fourier series of such type of function. So we found that in this way, by seeing the conditions of symmetry, we can just predict which terms will be missing in the Fourier series and which coefficient will be present in the Fourier series of such a type of function. Hope this topic is clear to all of you.